Okay, welcome to another session. Again, we are looking into the Fourier series, and we are working out some more problems on Fourier series. So I said in the last session, we worked problems on Fourier series when they give the signal and ask us to find in terms of the exponential Fourier series. So now we will look into problems on trigonometric Fourier series. And as I said, why we have to study Fourier series? If you want to understand the frequency analysis, if you want to perform frequency analysis, or what is the frequency content of the signal, uh, or we want to find out what is the power or the for the signal, we want to go to the frequency domain and we can analyze the function in the frequency domain. For that, we apply or we use the Fourier series. And Fourier series is applied for periodic signal. And we are talking of a continuous time periodic signal. Okay. All right. Now let us solve some more problems. In this session, we will be solving problems with using trigonometric Fourier series. Okay. So sorry for that. So we know that the signal x of t can be written in terms of the trigonometric Fourier series as a naught plus sigma n equals 1 to infinity a n cos n omega naught t bn sin n omega naught t. All right. So this is the standard form of writing the Fourier series. You know that you can go on getting infinite number of sine and cosine terms. Uh, so we can represent any signal, any periodic signal in terms of sine and cosine. So previously we had represented using the complex exponential. Here we are going to write directly in terms of sine and cosine terms. All right. So where A naught is nothing but the DC value or the constant value, and the ANs are the coefficients for the cos, and BNs are the coefficients for the sine terms. All right. So how do we write it in terms of the uh, complex exponential? So instead of Cn or Ck, I've written here in terms of Fn. So these are all the different notation, because again an we are using for the what you call the Fourier series in terms of trigonometric series, so we don't want to confuse with that. So therefore we are simply representing the ck as fk here, fn here. All right. So the formula is the same one. Okay, so this is in terms of the complex exponential. This is in terms of the sinusoidal or the trigonometric representation of Fourier series. Okay, now we will solve problems using trigonometric Fourier series. Now this is a signal given and we have to find the Fourier series, not the complex exponential. By using this formula, we have to use this formula to find the Fourier series coefficients. All right. Maybe in your maths class, I think this is the formula you would have used. So they would have taught you from the trigonometric Fourier series point of view, but we have studied the complex exponential Fourier series. Now we will get a hold on the uh, trigonometric Fourier series usage also. Okay, so this is the signal given. So what is the period of this? 0 to t naught is a period. What is the amplitude? Is minus a to plus a. So from 0 to t naught by 2, it has an amplitude of plus a, and t naught by 2 to t naught, you have an amplitude of minus a. Can you tell whether the signal is even or odd? And is it real or imaginary? The signal is purely real. There are no J terms in that. All right. And the signal is an odd signal. All right. So the signal is not an even signal. The signal is an odd signal. So okay. So this is an odd signal. Okay. For such a signal, we have to find the Fourier series by using trigonometric function. Okay, so the a value is given as 3 in the problem, and the period t naught also they have given it as a 2 pi. Okay, so we don't have to break our head in terms of t naught, what is t naught, what is a. They have given here so that we solve our problem a lot more simpler. Okay, so this is the problem we have to find. So what is the x of t? X of t, let us write what is in terms of these values. So x of t, if you take from this is 0 to 2 pi, right? What about this? This is pi, minus pi, and this is plus pi. So we can integrate from minus pi to plus pi, or 0 to 2 pi. From minus pi to plus pi also it counts one interval or one period, and 0 to 2 pi also counts one period. So the period should be equal to 2 pi, whether we take from minus pi to plus pi or 0 to 2 pi. Anyway, it should be over one period. All right, so here we are taking it as, so the signal is having an amplitude of minus 3 between the, in the interval minus pi less than or equal to t less than 0. So this is minus pi and 0. The amplitude is minus a means minus 3. From 0 to pi, so 0 to pi, the amplitude is plus a, and plus a means plus 3. So we have written it in terms of numbers instead of writing it as a and t naught and so on. We have written in terms of pi and amplitude, the number. Okay, 3. Okay, so as I said, it is an odd signal. So we see that when the signal is real and odd, the condition is it will not have the cos terms, it will have only the sine terms. All right, so since the x of t signal is odd symmetric, so a naught, there will be no constant term, and which is the odd term here. So sine is an odd function, right? Cos is an even function, so it's an odd symmetric, so therefore these two terms will be zeros. So therefore your bn, only the bn values you have to find out. They are called the uh, coefficients, the Fourier coefficients for the sine function. All right, for the sine uh, trigonometric sine function. Okay, so this will be equal to 4 by, so we have to integrate it over the period. So it will be uh, minus pi to 0, minus pi to 0, which will be 4 by 2 pi, minus pi to 0, minus 3 sine n t dt. Okay, so this is what we will be integrating. So when we integrate this, we get integral of sine is a cos. So we get this 6 pi cos nt by n. And then when we substitute the values, so we get 6 by n pi into 1 minus cos n pi. And you know that when n takes all odd values, uh, the function is minus 1. So minus of minus 1 here, minus of minus 1 will become plus 1. So this term will exist. When n takes all even values, cos will be plus 1. So 1 minus 1 will become 0. So therefore the function will be 0 for n even, and for n odd, it will be equal to, for any n, this is always minus 1, right? So minus of minus 1 become plus. So 1 plus 1 is 2. So 2 is 2 into 6 is 12. So you get this as 12 n pi for n odd. All right. So that will be the bn term. So we have to put back in this equation and find out what is the uh, what is the trigonometric Fourier series expansion. All right. So when you put the value of bn, it is nothing but 12 by n pi. So since we have the summation for n, so n will be inside, and so this will turn out to be sigma n equals 1 to infinity sine 2n minus 1 by 2n minus 1, and for the sine you'll have the t term. All right, so that will be the expression. Now let us take another problem. Okay, so here we have a signal which is we have to again we have to find the Fourier series representation for the periodic signal with period t naught is equal to 2. All right, and here x of t is defined for -1 to +1. All right, but from the interval -1 to -half, the signal is 0, and -half to +half only it exists, and again from +half to +1 it is 0. So it repeats after this. So that is what it means. So we are telling over only one period. Okay, so let us, is it a periodic signal? Yes, it is a periodic signal, and it repeats after this interval. And is it real? Yes, it is real. So therefore we have to find the Fourier series. So let us see first of all what is the t naught given. So t naught is given as 2. So what is the omega naught? That is the fundamental fundamental frequency. Omega naught is given by 2 pi by t naught. So that will be equal to pi. So omega naught will be equal to pi. So that is the fundamental frequency. So in the previous problem, I have missed to indicate that fundamental frequency there. Okay, so therefore, since x of t is an even symmetric, so you can see that it is even symmetric. It exists from minus. So at 0, when you at t equals 0, that means along the y-axis, if you fold along the y-axis, the signal is even, right? So this is an even signal or even symmetric signal. So therefore, x of t is an even symmetric. So when x of t is even symmetric, the sign terms will be 0. And we have to find out what is the a naught, that is the constant term, and the an. So for a naught, we have to integrate, but the a naught function value is 0 for -1 to half, -1 to -half, and from -half to +half, it is the cos, and from half to +half to +1, it is 0. So when you integrate this, so we get the different a terms. All right. So for a naught, we get this as -2 by 3 pi. So that will be the constant term. Now for n, different values of n, we will calculate. So for n equals 1, a1, as we said, the b terms are all zeros. So only the a terms will remain. So a1 will be equal to, so when n is 1, so this term becomes cos integral of cos 3 pi t cos pi t dt. And when you integrate it, this is equal to 0. When you take for 2, n equals 2, then you get this as 6 by 5 pi after substituting the limits. Next, when you calculate for 3, n equals 3, so you get the value as 1 by 2. How do we integrate this cos into cos? Anybody have any idea? Yes. So this is nothing but cos A cos B can be written as, in terms of the trigonometric identities, you can write this, the formula, the trigonometric, the half angle formulas, and those formulas. You can use it and convert the product term into the sum term. All right, and integrate it. So that is how we have got these answers here. Okay, so for the next, when you continue like this, and what will be for n? So we see that it will be 6 cos n pi by 2 n square pi minus 9 pi. So that will be the answer that you get for nth term. So it will go on. So therefore now we have to put back in the actual formula. Actual formula is x of t is equal to a naught by 2 plus sigma n equals 1 to infinity, and only a n cos n pi t will remain, because bn term is all zeros. So therefore, if you put back what is the different values, a1 is 0, but a2 is 6 by 5 pi, and when n is equal to 2, that becomes cos 2 pi t, and 1 by 2 is for a3, cos 3 pi t, and we can generalize the other. For n equals 4 to infinity, we can generalize and write it in this form. All right, so this is the Fourier series representation using the trigonometric functions. Okay, so now let us take another problem. We want to find the half-wave rectifier signal, and we want to express the output of the half-wave rectifier signal in terms of the trigonometric Fourier series representation. Okay, so we are applying again a x of t as an input, which is equal to cos 2 pi t, and cos 2 pi t is an even function, so we are going to apply the even function for the input. So what will be the output? Output will be also an even function, because it's the cosine and it's a half wave rectifier. So you see that this will be when you fold it along this point here, or if you take it and here is your 0, so if you fold it along 0, so it is an even function. Okay, so therefore this is an even function, and we can express this in terms of the Fourier trigonometric Fourier series. So we see that y of t, which is the output, is real and even function, and its Fourier coefficients are also real and even, just like we saw in the previous problem. So what is the fundamental period? T naught is equal to 1. As you can see from here, it is equal to 1, from 0 to 1. Okay, so omega naught will be equal to 2 pi by T naught as equal to 2 pi. So the fundamental frequency omega naught will be equal to 2 pi. So therefore, what will be the average value? A naught. So if you integrate this signal, you will get this as 1 by pi. So we have to integrate it from, so you see here, we are integrated from minus 1 by 4. What is minus 0.25? Is minus 1 by 4. And plus 0.5 is plus 0.25 is plus 1 by 4. So we have to integrate from minus 1 by 4 to plus 1 by 4. We are integrating the function. So we get the A naught value as 1 by pi. Next, we want to find the n, an. So that means all the bn terms will be all zeros. So only an terms exist. Ans are the coefficients, the coefficients for the cost terms. All right. So therefore, an will be equal to 2 by 1 integral minus 1 by 4 to plus 1 by 4 cos 2 pi t and cos n omega naught t dt. So we can write this as cos of a plus b into cos plus cos of a minus b by 2, right? So we can write it like that, and then we integrate it. So you get in terms of sine, and when we apply the limits, we get this as, and after simplifying, we get this term as 2 cos pi n by 2 divided by pi into 1 minus n square. So once we put this into the the trigonometric Fourier series formula, x of t is equal to a naught by 2 plus sigma n equals 1 to infinity a n cos n pi t. So there we get a naught value is 1 by pi. So we get this is 1 by 2 pi plus sigma n equals 4 to infinity, this formula. Now this is the Fourier series representation of the half-wave rectifier in terms of the trigonometric functions. That is the trigonometric Fourier series function. All right. So far we have seen the Fourier series, and we can refer more books and solve more problems. So thereby you get a better hold on this. Uh, so so again, why we have Fourier series, so that we can analyze the frequency content of the signal. So how do we take the signal to the frequency domain? By taking the Fourier series. So we by applying the Fourier series, we will know the frequency content of this signal. So how we can analyze the signal in the frequency domain. So this is for the periodic signal. So if we have a periodic signal, we apply Fourier series, and it is a continuous time signal. So this Fourier series, whatever we have studied so far, it is also called as CTFS, or the continuous time Fourier series, because we are dealing with a x of t, which is a continuous time signal. Now you can also have DTFS, that is discrete time Fourier series. So if you are dealing with a Fourier series which is discrete in nature, so whereby you, instead of x of t, you represent as x of n, where n is a discrete function. So as I said, x of n means it will exist only for the integer values of n, not for all values, not for fractional values of n. So therefore, for such a signal, we have a Fourier series, so that is called as a DTFS. So Fourier series, again, can be for a continuous time signal or a discrete time signal. Anyway, the discrete time signal is not there as far as the syllabus is concerned. So, but for your information, you can remember that Fourier series, you can apply both for the continuous time signal as well as the discrete time signal, but it has to be periodic signal. Now, what about the non-periodic signal? Because most of the signals what we see are all non-periodic in nature. That means we start at some time. Now, when I speak the words again, when we analyze the speech signal or the music signal, it starts and ends. It does not exist for all time, right? So therefore, it has different frequencies. So how do we analyze such signal? So for such signal, we apply what is called as Fourier transform. So as I said, if you talk of the periodic signal, we analyze such signal and find out the do the frequency analysis for such periodic signals by using Fourier series. Now, if we have non-periodic signals, how do we analyze the how do we do the frequency analysis of that? That we do by using Fourier transform. So that we'll consider in the next class. So we will look into the Fourier transforms. So that will be the part B. So this Fourier analysis in module in unit 2 has two Fourier analysis you have to do. That is, one is a Fourier series and Fourier transform. And for a periodic signal, you use Fourier series. When you talk of a non-periodic signal, then we use what is called as Fourier transform. So please remember that for periodic signal, we use Fourier series, and for non-periodic signal, we use Fourier transform. All right. So with that, we will wind up this and take up the next topic, Fourier transforms. Thank you.